the name of Almighty God, I'm Master Sankosha, and today I want to talk about multibody dynamics in quantum multiphysics simulation software. Now I want to go through the axial rotation constraints. Axial rotation constraints are available for the ball joint and slot joint features. The relative rotation on which the constraint is applied is the relative rotation of the destination attachment about its own axis. The constraint can be applied as both the upper and lower limits on the relative rotation of the destination attachment about its own axis. This constraint is uniquely defined as long as the maximum relative rotation is less than 180 degrees. You prescribe the maximum and minimum axial relative rotation of destination attachments, SOA maximum and SOA minimum. The cousin of the relative axial rotation of the destination attachment is written as cos zeta is equal to 1 minus 2 multiplied by ER multiplied by E df1 to the power of 2 multiplied by 1 minus ER to the power of 2. ER is equal to 1 divided by square root of a BR to the power of 2 plus CR to the power of 2 plus DR to the power of 2 multiplied by the matrices only one column BR, CR and DR. Here IR, BR, CR, DR represents the relative quaternion and ER is a normalized relative rotation axis. The activation conditions for the maximum and minimum relative axial rotation constraints are written as cos zeta is less than cos zeta maximum multiplied by ER multiplied by EAD1 is greater than 0. The default value computation for the penalty factor and maximum allowable time step is the same as for rotational constraints. The momentum of inertia for the source and destination components are computed about an axis. This is passing through the center of joint and is parallel to the destination axis. The modified penalty factor, constraint, moment, and virtual work contribution are similar to the inclination angle constraints. The only change is in the constraint activation conditions. Now I want to go through the theory for joint locking. The locking feature is used to lock the relative motion between the two components connected to a joint. You specify limits in the relative motion in the form of an upper and lower bound. This can be interpreted as an imaginary object like a snap hook that locks one of the free relative degrees of freedom of the destination attachment when it reaches the limiting value. The locking feature differs from constraints in a sense that the value of the particular joint degrees of freedom becomes constant for the rest of the analysis after it attains its prescribed limiting value. The translational locking, rotational locking, inclination angle locking, and axial rotation locking types are discussed in this section. Now I want to go through the translational locking. Translational locking is available for the prismatic joint, cylindrical joint, screw joint, planar joint, slot joint, and reduced slot joint features. In this locking type, a lock is applied to the relative displacement U. When the lock is active, its relative displacement becomes constant at the prescribed limiting value and relative velocity goes to 0. If Locke's conditions are active for all the joint degrees of freedom, then the source and destination attachment moves as a single object. You prescribe the maximum U max and minimum U minimum limits of relative displacement. The activation condition for locking is U is greater than U maximum, is less than U minimum. Locking is implemented using a penalty method where the relative velocity is forced to become zero for the rest of the time. There is a loss of energy during locking, which can be interpreted as the energy given to the imaginary object responsible for locking. The degrees of freedom due to locking phenomena. Stress waves are generated in the flexible components. You can add damping to the problem to suppress the unwanted stress waves. The locking indicators IAU max and IAU mean are ODE variables used to ensure that the lock is active for the rest of the simulation. The values of the inclinators are switched from 0 to a non-zero value when the lock is active. Through the following questions, we have a derivative IA UMX based on the time is equal to U greater than UMX, and derivative of IA minimum based on the time is equal to U less than U minimum. The force required to lock the relative motion is FAU is equal to minus PAU1 multiplied by U minus UMX minus PAU2 multiplied by derivative of the U based on the time when IAUMX is greater than the 0 minus PAU1 multiplied by U minus U minimum minus PAU2 multiplied by derivative of U based on the time when the IU minimum is greater than 0 unless we have 0 value, where PAU1 and PAU2 are the parameter factors. PAU1 can be interpreted as a spring constant, and its default is a function of an equivalent Young's modulus and geometric dimensions. PAU2 is a damping coefficient, and its default is 10 millisecond times the value of PAU2. These penalty factors are inputs and you can modify them as required. The value of the penalty factor PAU2 controls the rate of the decay of the relative velocity. A large value gives a high rate of decay but can cause convergence problems. To enforce the locking condition, a contribution is added to the virtual work. Delta W is equal to FAU multiplied by delta U. In the case of a planar joint, the relative displacement is locking along a user-defined axis. The locking direction oriented in a plane perpendicular to the joint axis. The relative displacement in the locking direction U1 is equal to U2 plus U3 multiplied by RS source multiplied by E1, where E1 is the normalized locking axis given by the user. Rotational locking is available for the hinge joint, cylindrical joint, screw joint, planar joint, and reduced slot features. The theory of the rotational constant is similar to what is described above for translational locking. Here, the penalty factor should be considered as a torsional spring. Inclination angle locking. Inclination angle locking is available for the ball joint and slot joint features. Here, the lock is applied on the inclination of the destination axis relative to the reference axis. The inclination angle or polar angle, the ODE variable used as a locking indicator, is computed from derivative I theta max based on the time is equal to cosinus theta is less than cosinus theta maximum. The moment required to apply inclination angle lock is written as m theta is equal to pi theta 1 multiplied by cosinus theta minus cosinus theta maximum plus p theta 2 multiplied by derivative of cosinus theta based on the time multiplied by sinus theta maximum when I theta maximum is greater than 0 unless we have a 0 value. To apply the lock, virtual work contributions are added for the cosine of the inclination angle. Delta W is equal to m theta delta theta is equal to minus m theta divided by sinus theta multiplied by delta cosinus theta is almost equal to minus m theta divided by sinus theta maximum multiplied by delta cosinus theta. Axial rotation locking. Axial rotation locking is available for the ball joint and slide joint features. Here the lock is applied to the relative rotation of the destination attachment about its own axis. There are two the variables used as locking indicators. They are updated using derivative of I max based on the time is equal to cosinus theta is less than the cosinus maximum multiplied by ER minus ED1 greater than 0. The moment required to enforce the lock of the axial rotation is such as this formula. To apply the lock, a mutual work contribution is added for the cosinus of the axial rotation of the destination boundaries. Delta W is equal to m zeta delta zeta is equal to minus m zeta divided by sinus zeta multiplied by delta cosinus zeta is equal to minus m zeta divided by sinus zeta maximum multiplied by delta cosinus zeta when I zeta maximum is greater than 0. when I is at a minimum is greater than 0, we have a minus m etc. divided by sinus etc minimum multiplied by delta cosinus etc. Theory for springs and dampers on joints. You can use the spring and dampers feature to apply a spring or dashboard to act under relating forces in a joint. A dashboard can be used to account for various kinds of losses at the joint. The spring can be given a period for deformation so that the spring equilibrium position is not the same as the initial state. The translational spring and damper, rotational spring and damper, inclination angle and axial rotational spring and damper. Versions of this feature are discussed in this section. Translation spring and dampers. The translation type of spring and damper is available for the prismatic joint, cylindrical joint, screw joint, planar joint, slot joint, and reduced slot joint features. The spring force, which is proportional to relative displacement, is Fa is equal to minus chi u multiplied by u minus u0, where chi u is the spring constant and u0 is the pre-deformation. You can also specify the spring force as function of extension explicitly as Fa is equal to minus Fs multiplied by Us, where Us is a spring extension. The damping force, which is proportional to the relative velocities, Fd is equal to minus Cau multiplied by U pre, where C is the damping coefficient. The virtual work contribution is delta W is equal to Fae plus Fad multiplied by delta U. In the case of joint, planar joint springs and dashboards are attached along user-defined axes oriented in a plane perpendicular to the joint axis. The spring axis and dashboard axis can differ. The forces are proportional to the relative displacement along the spring axis Us and relative velocity along the dashboard axis via dp respectively. Us is equal to U2 U2 plus U3 U3 plus R source Us. Nu dp or damping is equal to nu do E2 plus nu3 E3 multiplied by R source damping, where EAS is the normalized spring axis and E damping is the normalized damper axis. Now I want to go through the rotational spring and damper. The rotational type of spring and damper is available for the hinge joint, cylindrical joint, screw joint, planar joint, and reduced slot joint features. The theory the theory for rotational spring and damper is similar to what is described above for translational spring and damper. All translational quantities are replaced by corresponding angular quantities. Now I want to go through the inclination angle and axial rotation spring and damper. The inclination angle and axial rotation types of spring and damper are available for the ball joint and slot joint features. The spring and damper here can affect two types of relative motion. The inclination angle and the axial rotation of the destination attachment. The inclination angle and axial rotation are computed as theta is equal to r cosinus of minimum maximum cosinus of theta and minus 1 theta is equal to r cosinus of minimum maximum cosinus of v minus 1 and 1 multiplied by AR ADA1 greater than 0 minus AR multiplied by ADA1 is less than 0. The definitions of inclination angle and axial rotation as well as the expressions of cosines are discussed in the inclination angle constraints and axial rotation constraints sections. As these rotations are computed using the inverse cosine function, they are unique as long as the magnitudes of the actual rotation theta and zeta are less than 180 degrees. The spring and damping forces are for both to those used for stronger rotational spring and damper theory for prescribed motion and joints. With prescribed motion, you can control the relative motion in a joint either by prescribing the displacement or the velocity. This is useful when the degrees of freedom in the joint are not free but are a noun function of time. This is common in the field of robotics. For example, the translation of prescribed motion and rotational prescribed motion version of this feature are discussed in this section. Now I want to go through the translation of prescribed motion. Translation of prescribed motion is available for the prismatic joint, cylindrical joint, screw joint, planar joint, slot joint, and reduced slot joint features. As constraint is added to prescribe the relative displacement in the joint. If no reaction forces are computed, then the constraint is enforced as a point-wise constraint. U is equal to UAP, where UAP is prescribed relative displacement. If reaction force computation has been requested by selecting a valid reaction forces, then a weak constraint is used. An extra degree of freedom, or a F, is added for the reaction force. The contribution to the virtual work is U minus UAP delta RF plus RF delta U minus UAP. If a unidirectional constraint is used by selecting apply reaction only on joint variables, then the form of the virtual work is changed to U minus UAP multiplied by delta RF plus RF multiplied by delta U. When the relative velocity is prescribed, an extra equation is added to find the relative displacement by integration of the relative velocity. Derivative of UAP based on the time is equal to nu AP, where nu AP is prescribed. Relative velocity and UAP is the velocity integration variable, which then is used in the constraint. In case of a stationary study, the relative displacement in the joint is constrained to zero. You can also set a deactivation condition on prescribed motion constraints. Once the specified deactivation condition is fulfilled and the deactivation indicator expression IUP, a Boolean variable is set to zero. True, the constraints are removed from the system. This makes the previously prescribed joint degrees of freedom free. In the case of the planar joint, the relative displacements or velocities are prescribed along two axes oriented in a plane perpendicular to the joint axis. The first axis is specified by the user, while a second axis in the same plane and orthogonal to the first axis. The relative displacement along prescribed motion axis and along its orthogonal direction can be written as UAP is equal to U2E2 plus U3E3 multiplied by R source multiplied by EAP. EAP2 is equal to U2E2 plus U3E3 multiplied by E1 multiplied by R source EAP, where EAP is a normalized prescribed motion axis. Thank you so much for watching my tutorial video on today. Today is the 8th day of June 2026. Time is 7:15 o'clock in the afternoon. Also, you can download the predefined and proper related capsule multiphysics simulation file from github.com/masterscript.